Welcome. My name is Randy Ellis. In this session, we'll recall some prerequisite material regarding basis vectors of a vector space. The main concepts for this session are vector space by means of specification rather than by means of restriction, what spanning vectors are for a vector space. A basis is a minimal set of such spanning vectors. We'll briefly recall the RREF of a matrix, and we'll explore how the RREF relates to both basis vectors for the column space of the matrix and to the null space. So, what we mean by specification is this. Suppose we have a vector space V, and each vector in it has m entries and they're real numbers. Specification can be either by restricting this larger set or constructing. And we want to view this construction method. So for example, suppose that you have vectors that have 3 entries each, size 3. A restriction might be that all of the vectors have to be orthogonal to this given vector. And a construction is that the vector space is all linear combinations of these two vectors. A spanning set of such a vector space is it could be infinite, but for us it's a finite set of vectors. So if we have a matrix that has m rows and n columns, we can view this as n vectors, each of size m. And each column of A can be viewed as a vector. So what we mean by a spanning set is that if a vector is in the set, then there exists a set of weights such that the vector is a weighted sum of the columns of the matrix. So alternatively, if we have a set of n weights, then using those weights in a linear combination of the columns of the matrix, we get something that's in a vector space. So for example, for that previous vector space, we could take the vectors and we could put them in a matrix in this form. Now a basis set is for a vector space that is composed of vectors with m entries each. A basis set for the vector space has the minimum possible number of vectors that you need to span the space. So for our previous example of a vector space, a span is the columns of that matrix A. A basis would be any two of the 3 vectors that are in this spanning set. But we can't have all 3 because we can see that, for example, this vector A sub 3 is a linear combination of A sub 1 and A sub 2. So a basis isn't unique, but it has to be sufficient. By not unique, I mean there's an infinite number of sets of basis vectors for a vector space, but each one of those basis sets has the property that a linear combination of those basis vectors is in the vector space. An orthogonal basis set is one. So suppose we have a basis for our vector space. We need n of these basis vectors to span a vector space that is n dimensions. An orthogonal basis is a set of vectors, and in subsequent courses we'll prefer to use the symbol Q for basis vectors. So it's a set of basis vectors such that if I is not equal to j, that is, if we have 2 distinct basis vectors, then they are orthogonal. So the dot product of 2 distinct basis vectors has to be 0. This is just saying that each one of these vectors has to be orthogonal to all the other vectors in the basis. An orthonormal basis is a particular kind. It's an orthogonal basis such that every vector has a unit magnitude or unit norm. So each basis vector, this is the best kind of basis, an orthonormal basis. By best, I mean that it has certain numerical properties that we will prefer. So what does this look like geometrically? Well, suppose that we have a vector space that's a subset of the coordinate space of size m. What this would look like is a basis vectors are spanning, so here I've shown basis vectors for the entire real space. So here I've stopped at 3 because beyond 3 my illustration capabilities are pretty much to be disregarded. So here we're showing an example of a R3 illustrated, but in general this would be Rm. And then you might have a basis set which is just a subset. So here I'm picking two linearly independent vectors and saying that those two linear independent vectors span the vector space V, and that subspace is within Rm, and these two distinct vectors constitute a basis. The dimension of a vector space is the number of basis vectors you need to span it. So some authors will, or presenters, will use the word dimension to also refer to vectors. We prefer to say that the size of a vector is the number of entries in it, and the dimension refers to a vector space. So vectors have size, space has dimensions. And one way that this is often written is we can say, what is the dimension of the vector space? So the vector space can be an argument of a map. So what is the rank of a matrix? Well, suppose now that we're thinking of as a matrix, and the columns span some vector space. The dimension of the column space is some value. The rank is the number of linearly independent columns of A. So the rank is the number of independent columns, and that turns out to be the dimension of the column space of the matrix. So this rank is often written as a function rank, which in something like MATLAB is a built-in function. And a fact is that the rank is also the number of linearly independent rows. So we're defining it as the number of linearly independent columns, but you can show over in mathematics that it's also the number of linear independent rows. So that means that the rank of A and the rank of A transpose have to be the same. Now, big recall, the RREF, the reduced row echelon form. So I won't go through this in detail because you can always refer to your prerequisite material for that. But for a matrix to be in RREF means the leading non-zero entry of every row is 1. The leading non-zero entry of a row is the only entry in the column. The leading non-zero entry of the second row and succeeding rows is to the right of the preceding row, and we put all of the 0 rows down at the bottom. So let's look at an example. So suppose we have a 3x4 matrix, and so this is the 3x3, and now I've added something on. So the RREF of this matrix, when we do the computations, is, so this is a leading 1, and it's as far to the left as possible. This is a leading 1. It is to the right of this one and has zeros up. This is not a leading 1. And so there can be something non-zero above it. This is a leading 1. It has to be to the right of this one, and all the entries above it have to be 0. So I commonly compute this using MATLAB. Now, the RREF can be used to select basis vectors of the column space of the matrix. So a fact, so by the way, a fact is something that's true, but I'm not going to prove it. You can go elsewhere for the proof. The fact is that these leading non-zero columns identify basis vectors for the column space. So taking this previous example, the RREF is this, and that means that 1 and 2 and 4 are linearly independent columns of the original matrix, and they are a basis for the column space of the matrix. let's recall a permutation matrix. So a permutation of a set of numbers is a way to rearrange the numbers. And we can represent this using a matrix. So the properties of a permutation matrix are each entry is either 0 or 1, and then there's two simple rules. There's exactly a single 1 in each row and exactly a single 1 in each column. What this means is it's an orthogonal matrix, and the inverse is the transpose. So what that means is if we want to undo the permutation specified by P, all we have to do is look at the transpose of the same matrix. So to permute the rows of a matrix, we pre-multiply by a permutation. To permute the columns, we post-multiply by the permutation matrix. Now, the REF has a permuted form. This is deep details that you probably don't need to know to proceed in the courses that I teach, but this is cool stuff. A fact, so another thing that's true I'm not going to prove, is we can permute the columns of the REF so that it is the REF with permuted columns can be represented as the identity matrix and a matrix that we're going to just call F. Now, this identity comes from this leading ones stuff. So if you recall that matrix we had 1 0 0 0 1 0 2 1 0 0 0 1, and we can permute those last two columns, and then we get the identity matrix, and then this final thing will be 2 1. So we may, in the REF, we may or may not have a row of all zeros. So it turns out that the null space is linear combinations of this. Is to find the null space of this permuted form, what you do is you negate this F part, and then you append the identity if needed. And if the REF has no zero rows, then there is no identity block in this permuted null space. So let's go through an example. So let's take that previous one. If we permute the REF as I suggested, this is the permuted form that we end up with. So this is the identity. This part is the identity. This 2 1 vector is the F. That's the zero block. This is the specific permutation that we have, and that's what we get. So the null space is any multiple. We negate this 2 1 0, so we put -2 -1 -0 0, and then we append the identity, and in this case it's just a 1 because it's a 1 by 1 that we need. And then if we permute that, you can verify that the null space is this vector Z4. What does this look like geometrically? Well, now let's think of the matrix as being a map. So it's a linear map from an n-dimensional space to an m-dimensional space. And the null space, that script n, is the set of all size n vectors that get mapped to a size m zero vector. So what that looks like is this. If we have our space of our coordinate space of size n, and we have a coordinate space of size m, what happens is that there's a subspace in that size n vector space that gets mapped exactly to the origin or to the zero vector in the m-dimensional space. One way that we could say is that if z is a vector in the null space, that specific z gets mapped to the zero vector in this size m space. Now let's go through a slightly more complicated example. And I've computed this, so you don't have to try to do this by hand, although you're certainly welcome to. Now let's make the matrix a little bigger. And when we make it a little bigger, what we find is that the REF is now this. It starts looking the same. So 1 0 0, which is what we had before, 0 1 0. This is a non-leading one, so it can have something non-zero above it. This is a non-leading one, so it can have something above it. And this is a leading one, so it has to have zeros above it. So what this means is that now columns 1, 2, and 5 are a basis set for the column space of this matrix A5. And specifically, the permutation order that we would compute is we would put 1, 2, 5, and then because we have to settle on some permutation, what we'll do is say we'll then take the non-leading entries and we'll take them in the order. So this one appears in order, this is 3 and then 4, and that's the way that we'll set up the permutation. What this looks like in the permuted form is this. Now what we have is this part is the identity matrix, and now F is a 3 by 2 matrix, and then this is the permutation that accomplishes the 1, 2, 5, 3, 4, and this has this standardized form where here we just don't have this block of zeros. And so the null space is any linear combination. Now we take this entire block here and we negate it, so that becomes this 3 by 3 block here, and then we append the identity, which is now a 2 by 2, and then we would apply the same, we would undo the permutation of the variables that we had, and what we could do is compute a basis for the null space of the original matrix A5. So, how do we summarize this session? Well, if we have a linear map that we're representing as a matrix, the column space is a subspace of R sub Rm. The null space is in Rn. The REF is one way to find a basis for the column space. The permuted REF gives us a basis for the null space. And the null space is a map itself of it, so it is all of the vectors in the n size n space that map to 0 vectors in this Rm space.